Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
Today we are diving into one of the most iconic intellectual battles in the history of science. Picture it. The year is 1927. The place,
Brussels,
the event.
the fifth Solvay Conference, a meeting of the greatest minds in physics.
Yeah, we're not kidding. This was no ordinary gathering. Names like Einstein, Bohr, Heisenberg, Dirac, Curie, and Planck were all there. If you don't know physics but you know a bit of Marvel, it was like the Avengers crossover but in science.
But this wasn't just a meeting of geniuses patting each other on the back. This was a battleground where two towering figures, Albert Einstein and Niels Bohr, locked horns over the nature of reality itself.
So let's imagine a grand conference hall in Brussels. The room is buzzing with discussions, and there are giants of physics like Heisenberg and Bohr that have just wrapped up their presentation, where they boldly declared just a few seconds ago that the fundamentals of quantum mechanics are settled. Period.
But then you see Einstein sitting quietly and not saying a word at all. Before the conference, he downplayed his role and proclaimed himself as an observer. But then Bohr echoed that same confidence, insisting that quantum mechanics was the final word.
So, just to note that while aspects of these debates continue even today, Einstein's main goal was to take down the ideas of complementarity and the uncertainty principle, concepts upon which many of the most unsettling aspects of quantum mechanics hang.
Picture this, it was like an elaborate game. Einstein would offer brilliant thought experiments that violated complementarity and the uncertainty principle, and Bohr would have to continuously dismantle them to keep his understanding of quantum mechanics alive.
Yeah, but then later, Bohr reinstated the idea that the fundamentals of quantum mechanics were settled. And at this, Einstein finally got up and walked over to Lorentz, who was running the conference, and he said, "Despite being conscious of the fact that I have not entered deeply enough into the essence of quantum mechanics, I'd like to present some general remarks."
By which he basically meant, may I please show Bohr precisely how wrong he is. I don't know much about quantum mechanics, but I do have something to say, something like that.
Yeah. So he walked up to a chalkboard and he proposed a mechanism that utilized the idea of conservation of momentum to again violate the uncertainty principle of Bohr.
His argument went something like this. So imagine Young's double slit experiment, which was spoken about in episode 8
Yep,
about
8.
quantum entanglement. So you put another barrier with a single slit in it between your beam of light and the double slit wall. And when you fire your light through that slit, we have to treat it as a waveform.
Yeah. So that means just as our original experiment, when the waveform passes through the two slits on the second wall, the two waveforms it produces will interfere with each other and give us the interference pattern that we're used to.
But since light is also a particle, the only thing that could have possibly deflected the particle like nature of the light would be bouncing off the first wall. There are no other variables or components in this experiment, so maybe that's the only possibility.
So imagine that the first wall is on ball bearings and can move. So in all directions. So by the laws of conservation of momentum, if we measure which way and by how much the first wall was moved by the impact of the photon bouncing off of it, we should be able to trace its path and tell which slit the photon is eventually going to go through in the second double slit wall.
If the wall was pushed, say, a little bit south, then we know that the photon bounced off of it and got reflected north, heading towards the northerly slit on the second wall, right?
But that can't be the case, nah. If you remember from our discussion of wave-particle duality, while basically everything operates like a wave and a particle, they don't operate as both as once at the same time
That's
at
right.
once.
That's right. So things like light are a possibility wave until that wave is collapsed by someone trying to measure it. At which point the stuff like the location of the photon within the space of the possibility has to be resolved. It's just like the Schrodinger equation that we talked about. When you make a measurement, the wave function collapses and you get more information about one aspect of the wave function, but you lose information about all the other aspects of it.
Yeah, also like a quantum computer where the superposition of the states is the answer, which you've spoken about earlier. So by that logic, we shouldn't be able to tell which slit on the second wall a photon will go through, particle-like behavior, and get an interference pattern for where those photons land on the screen behind it.
Because in order for the wave pattern to interfere with each other on the other side, the light would have to be acting like it was a wave as
Yeah.
it passed through the slits, right?
Yeah. So if we could observe both the wave aspects and the particle aspects of light simultaneously, That would violate the whole point which we made earlier, and thus it'll unseat the uncertainty principle.
But Bohr had an answer. He basically said that Einstein had set up a straw man here. He hadn't removed uncertainty, he had just moved the uncertainty from one place to another without even realizing it.
So you see, in order to measure how much rolling that first wall did, as a result of being hit with one singular photon, you'd have to know the exact location and the movement of the wall itself before the photon hit it.
And because we're dealing with only one photon here, you'll have to be incredibly precise. I mean, precise to the level that quantum rules kick in. And dealing at that quantum level means that we run into indeterminacy.
So you can't know both the momentum and the location of the wall with perfect accuracy. Uncertainty principle.
So, yes, Einstein's example would violate indeterminacy. But the only way his example works is if you ignore it in the first place.
So not bad for the first round. And over the rest of the conference, Einstein kept the energy alive and sparred Bohr in a spirited back and forth. Imagine it, two giants of physics that were turning the dining halls and hotel hallways into their own private debate stage. While the formal conference happened upstairs, the real action was actually wherever these two were hashing out so-called quantum mechanics of their own kind.
But as much fun as all of this sounds, Einstein wasn't fully satisfied. The next Solvay conference was set for 3 years later, and Einstein wasn't coming empty handed this time. He came bearing some gifts, or rather, a box of light.
So picture this. Einstein walked into the next conference and he said, kind of like a magician revealing his grand like bunny trick or whatever, he said to Bohr, imagine a box. Now this doesn't just isn't any box. It's lined with perfectly reflective mirrors. Inside, light is bouncing around. And it's got a clock. Because every good physics experiment needs a clock, right?
Of course.
But the point Einstein was trying to make was at a precise moment, the clock will open a tiny hole in the box just long enough for a single photon to escape.
Einstein then says, now weigh the box. Now cue Bohr, who immediately looks like he's seen Schrodinger's cat and knows the answer to the experiment. He starts pacing around muttering, it can't be true, it can't be true. Because here's the kicker. If you weigh the box before the photon leaves and then weigh it after, you'll know the mass of the photon. And thanks to Einstein's own equation, E is equal to mc squared, if you know the mass, you know the energy. But wait, isn't a photon massless?
Arey, you wait, no. Curb your curiosity for a second. Here's where things get spicy. Okay. The uncertainty principle, famously, says that you can't know certain pairs of properties, like as we obviously said, position and momentum, with perfect accuracy. But that also applies to energy and time. According to the principle, you can't know the exact energy of a particle at an exact time. So Einstein box, though seems to break this rule, doesn't actually do that because the clock gives an exact time and the weight of the photon lets you determine its exact energy. So Bohr does what anyone would do when he was faced with an intellectual crisis. He just retreated to his room to panic in private. For hours, he sketched diagrams and imagined how the experiment might actually work, and he probably drank too much coffee and muttered ominously about the end of physics.
Then, just before dawn, Bohr gets his own eureka moment. With a smile and probably very bloodshot eyes, he finally gets some sleep. And the next morning, Bohr strides into the conference room, ready to reclaim his turf. He begins by acknowledging Einstein's setup. If a photon escapes the box itself must recoil slightly, thanks to the conservation of momentum. But here's the catch. Quantum uncertainty means that we can't precisely measure that recoil.
Yep,
Sure,
fair enough.
that's interesting, but Einstein's argument isn't about momentum. It's about energy and time.
And then Bohr drops the hammer. To weigh the box, he says, it has to be in a gravitational field. Now, because weight only exerts gravity, as we know,
Correct.
the twist Bohr brought into it was Einstein's own theory of relativity tells us that gravity distorts space-time. So that means any clock inside the box would be affected by those distortions, and time would get fuzzy, and we couldn't measure it with perfect precision.
In other words, basically, Einstein's clever thought experiment doesn't escape uncertainty, it just runs headfirst into it from another angle.
So before we give Bohr a full victory lap, let's be fair. Some physicists have since questioned Bohr's solution and they've suggested alternative interpretations, but for the time it was a solid rebuttal and it reinforced the quantum framework that dominates physics to this day.
You see, this isn't just a story about two geniuses debating the finer points of quantum mechanics. It's a reminder of how science moves forward through challenges, counter arguments, and occasionally pacing around and muttering like this can't be true.